The first session of the conference is given by Giulia Fanti. She's a postdoc here at UIUC-CSL, and the topic for her talk is anonymous message spreading in the presence of spies.
All right. Hi, everyone. Today I'm going to talk to you about anonymous messaging in the presence of spies.
It doesn't work.
It doesn't work. Okay, great. Thank you. So some people have important, sensitive things to say, ranging from whistleblowers to political activists. Other people have maybe less important things to say, but often they're equally sensitive on topics like religion, sexuality, or mental health. And the problem in both of these cases is that when people share their thoughts in online forums, like social media, they're often subject to repercussions, which could range from being socially ostracized by their peers to being physically imprisoned, especially in countries under authoritarian rule. And so the question that we want to ask is, how can we design systems that allow people to share their thoughts without fear of repercussion? And obviously that's a complicated question that relates to politics and psychology, but in particular we're interested in the technical aspects of this problem. And from a technical perspective, one thing we can do is to design systems that inherently provide privacy. So our goal is to design a network, like a social network, that allows a user to post a message, like on Twitter, without revealing their identity to a state-level adversary. So this topic has been of interest in industry for the last couple of years. We've seen the rise of a number of so-called anonymous messaging apps like Whisper, Secret, Yik Yak. And these apps basically let you post messages like on Facebook without revealing your identity. And so these apps have become extremely popular, especially in the college and high school age demographic, to the extent that Yik Yak is actually geo-blocked in a lot of high schools around the nation. So if you go into a high school, it just won't work. And these networks work more or less in the same way. They assume there's an underlying contact network. So in the case of Secret, that's a social graph. And note that this is overlaid on top of the underlying communication infrastructure, so the internet or the cellular network. And if a user, Alice, has a message that she wants to post, that message gets pushed to all of her friends in the social network. So the friends would see the message, but they wouldn't see who authored it. Now, if one of Alice's friends decides to like the message, it gets spread to the friend's friends, and so forth. So this message propagates over the network, but no single user can figure out who was the true source of the message. And that's the sense in which these networks provide anonymity. But if we look under the hood at what's actually happening, anytime Alice posts a message, that message is first going to a central server, which will then forward her message to all of her friends. So the problem here is kind of clear, right? This central server sees everything. It knows who's a message author and when messages are forwarded. So inherently, centralized networks are not providing any kind of real anonymity. Okay? But the problem isn't just that this server gets to see who authored what messages. The problem is that centralized architectures enable data leaks, both intentional and unintentional. So we've seen over the last couple of years a number of high-profile data leaks. So for example, Whisper is a network that is entirely dedicated to secrecy and anonymity, but there have been rumors that it's actually feeding its users' location information to the Department of Defense, without its users' consent, of course. And then there have also been a number of high-profile data breaches over the last couple of years that are enabled by these centralized architectures. So what we really want to do here is to avoid trusting servers to do the right thing and be good stewards of our data. We would much rather throw this centralized architecture out the window and design distributed messaging mechanisms that protect users against de-anonymization, even against powerful state-level adversaries. Okay? So what kind of adversaries are we talking about here? An adversary could do a number of different things. So in increasing order of power or magnitude, we considered a number of different adversaries. The first of these is a snapshot adversary. a snapshot adversary gets to see which users have received a given message at a given point in time. So for example, if I organize a protest on social media and the government gets wind of it, and they don't like it, they could show up to the protest and see which humans are physically present. And that would be like a noisy image of which users in the social network got the message. Okay? The next adversary we consider is a spy-based adversary. And this is a technique that's actually used by police agencies around the world, including places like Iran and even the United States. And here, the police agency will put fake or corrupted accounts into social media networks and use these accounts to effectively spy on other users. So if someone is posting anti-government rhetoric, that will get reported back to the authorities. So that's the second adversary we consider. And the most powerful adversary you could probably imagine is one that has full network oversight. So this adversary gets to see what traffic flows at what time to whom. And this is how we might model someone like the NSA, for example. And we're not going to explicitly consider this adversary because in effect, there's really not much you can do against that kind of an adversary using just algorithmic techniques. But I'd be happy to talk about that more offline if anyone's interested. We have some ideas on how to deal with these kinds of adversaries. So in this talk, I'm particularly interested in the second adversary, spy-based adversary. But it turns out we also have results for this first snapshot adversary. So cycling back to this objective, we're trying to design a distributed messaging mechanism that prevents message authors from being de-anonymized, even against a spy-based adversary. And I'll make the adversarial model more precise in just a second, but this is the high-level idea. So let me start by presenting to you a first-order solution, and then tell you why that doesn't work. So the first thing we might think to do is to replicate what's currently done in anonymous messaging apps in a distributed way. So by that I mean anytime Alice has a message, let's say she sends it directly to Bob and Mary without going through a central server first. Okay? And then if, let's say, Bob likes the message, he'll send it directly to his friends without going through a central server. So here effectively we're replicating the spreading mechanism of secret, or yik-yak or whatever, just in a distributed way. So, perhaps surprisingly, the adversaries I mentioned on the previous slide can still infer the source if you do this. And to understand why, let's think a little about how messages flow on social media. So let's say Alice is this red dot, and she's spreading a message. So most social networks today, including those anonymous messaging apps I told you about, spread content symmetrically, which means that all of Alice's neighbors will see the message, but maybe with some delay. Okay? And so let's say that when one of Alice's neighbors sees the message, they automatically approve it, and so it goes to their friends. And so we can observe the spread of this message over time, and we notice that it's spreading roughly in a ball that's centered precisely on Alice. Okay? So this randomized symmetric spreading is often modeled mathematically by a diffusion process over graphs. And this matters because there's been a lot of research in recent years in the epidemic source detection community on trying to find the patient zero of an epidemic. And this work, so for example, in the Ebola virus, you're trying to find the patient zero. And kind of the takeaway message of this work is that you can reliably identify the source of these diffusion processes. So basically, if I'm the adversary and I'm trying to find out who was the source of this message, I can compute the likelihoods of different nodes being the true source, and those likelihoods are much higher near the true source. So if I'm your authoritarian government of choice and I nab these four guys in the middle, with probability bounded away from zero, one of them is going to be the true author. Okay? So diffusion spreading, which is used basically in every social network today, actually has very poor anonymity properties. So this implies that that first order solution I told you about earlier really isn't going to work for us. So we need to do something different. We need to design an alternative spreading protocol that makes this kind of statistical inference difficult for the adversaries that I talked about earlier. So we're going to consider a spy-based adversary, like I mentioned earlier, and we model it as follows. each node in the network is a spy with probability p. And each spy is going to collect all of the metadata that it observes. So, for example, if Alice starts spreading this message, here Craig is going to report that he saw the message at time 1, and David is going to report that he saw it at time 2. Okay? These spies also know the underlying structure of the graph, and they also know the spreading protocol that you're using. But they cannot see individual instances of randomness that are drawn. So, in the face of this spy-based adversary, we would like to propose a scheme that makes it difficult for them to infer the source. Now, I'm not going to start from scratch because we've already done some work on designing a protocol that defends against a snapshot adversary, which, recall, gets to see which nodes observe the message at some point in time. And this protocol is called adaptive diffusion. And intuitively, adaptive diffusion breaks the symmetry of regular diffusion by spreading content fast in certain randomly chosen directions and slowly in others, in such a way that if the adversary were to compute the likelihoods of different nodes being the message author, those likelihoods are all approximately equal. And this allows us to show some provable anonymity guarantees for a snapshot adversary. Now, the question that we want to ask with regards to this talk is, how does this spreading protocol work against a spy-based adversary, which is in some ways more realistic than a snapshot adversary? So, to deal with this, I'm going to first explain to you how adaptive diffusion works on trees and show you why it's good against a snapshot adversary. And then we'll see what results we can show for a spy-based adversary. Okay? So, adaptive diffusion works by keeping track of two pieces of metadata, a node color and a level. And I'll explain what those parameters mean in just a second, but the intuition here is that we're trying to build an infected subgraph, or a subgraph of nodes who have seen the message, that is a balanced tree with a true source at one of the leaves. Okay? So if we think of this message spread as a ball, we want the source to be at the boundaries of that ball. Okay? So here, this level parameter, m, describes how far away a node is from the leaves of this infected subtree. So because we want the true source to always be at the boundary, we're going to assign it a level 0. All right. Now, in the first step, this source is going to choose one of its neighbors uniformly at random and assign it the color orange and the level 1. That always happens. And then from now on, we obey 3 spreading rules. The first is that if you are an orange node with level greater than 0, you're going to infect one neighbor with orange color and level incremented by 1, and the rest of your neighbors with a blue color and level decremented by 1. Okay? So that's rule number 1. And here we can see if you do that at time 2, this infected subgraph is a balanced tree with a true source at one of the leaves. Okay? All right, the second rule is that if you have level 0, you don't spread anymore. You're done. Okay? And the third rule is that if you're a blue node with level greater than 0, you're going to spread to all of your friends with a blue node that is decremented by 1. So here in this next time step, we see that this m equals 1 spread to all of its neighbors with blue nodes, and the orange node at m equals 3 spread to 1 orange and 1 blue. And here again, we see that at time 4, this infected subgraph is a balanced tree with a true source at one of the leaves. All right, so why does this matter? Why does this work? So if I'm a snapshot adversary and I come in and see only which nodes have seen the message, I know only that the source is at one of the leaves. So this tree has symmetry because of the underlying graph. And so I don't know which one of the leaves it's at. Now, and that means that all of the leaves have equal likelihood of being the true source of this message. So since the number of leaves in the graph is linear in the number of total nodes in this infected subtree, we get a probability of detection here that scales as 1 over n, where n is the number of total nodes in this infected subgraph. Is that clear? Okay. So, all right, so that's why this mechanism works for a snapshot at, yeah? Okay. Great. So the question was, you're assuming here that each node is agreeing to spread the information. Is that right? Okay. Whereas in practice, you can't predict if someone's going to like or dislike a message. And so this is actually a good point. And in our app that we've built, we deal with that by using some UI tricks. So in particular, we've built an app for Android. And so in order to see the next message, you have to either like or dislike a message. And so in that way, we kind of force people to give us feedback, which allows us to, which doesn't preclude the possibility of somebody disliking a message, but it at least gives us more information to propagate this message on. Okay, so given that this works for a snapshot adversary, we now want to ask, how does adaptive diffusion fare against a spy-based adversary? All right, and recall that for our spy-based adversary, we assume that every node except for the source is a spy with probability p. And each of these spies is going to see all of the metadata it receives. So for adaptive diffusion, it's going to see the color, the level, the timestamp at which it received the message, and it knows who delivered the message to it. Okay. Now, this is a hard adversarial model to deal with, because with probability at least p, the first node that I send my message to is going to be a spy. Okay. So what do I do then? This means that p is a lower bound, a fundamental lower bound on the probability of detection, regardless of how many nodes have seen the message in total. Okay. Now, by averaging over all of the possible configurations or locations of these spy nodes, we can compute an exact probability of detection for adaptive diffusion under this spy-based adversary. And that probability of detection is a hairy expression, but it scales as p plus little o of p. Right? And so just to show you visually what's going on here, this plot is showing the theoretical probability of detection for adaptive diffusion as a function of the spy probability p. And so this black line is that lower bound I told you about, which is exactly p. And this plot is showing us that as the degree of the underlying regular tree increases, we get closer to this optimal lower bound. And on the other hand, it's pretty easy to show that for regular diffusion, as the degree of the underlying tree increases, your probability of detection tends asymptotically to 1. So this might seem kind of weird to you, because here we're scaling a property of the underlying graph, whereas in practice your graph is fixed. But the point I want to make here is that in a lot of social networks, many nodes have high degree. So for example, in the Facebook graph, the median user has about 200 friends. So this is firmly in the regime where we would at least expect adaptive diffusion to perform well and regular diffusion to perform not well. But of course, these results only hold for regular trees. So to evaluate this intuition, we simulated the spread of both regular diffusion and adaptive diffusion on a subset of the Facebook graph. And so here I'm showing you the probability of detection for these simulations as a function of the spy probability. And so this black line, oh, I guess that didn't show up. This black line is, again, our lower bound on the probability of detection. And this plot is showing us that adaptive diffusion, which is the blue dots, is performing close to optimal, whereas regular diffusion has a probability of detection that's much higher and tending to 1. So this confirms our intuition that adaptive diffusion performs well both against a spy-based adversary and against a snapshot adversary, whereas regular diffusion performs quite poorly against both adversaries. So because of this, we think adaptive diffusion might be of practical interest. So like I mentioned before, we've built an Android app called Wildfire, which uses adaptive diffusion as its underlying message spreading mechanism. And so you can check it out on GitHub if you're interested. And this app is built on top of Talks, which is a peer-to-peer secure messaging app or platform. And building this app has kind of introduced a few questions that we weren't really thinking about while analyzing the theory of these spreading mechanisms. One of these issues is namespace resolution. So because we're using Talks as our underlying messaging platform, it becomes very difficult to know if namespace resolution is being done in a protected or compromised way. And so actually this issue of privacy-preserving namespace resolution is an active area of research right now. It's something we're looking at. And another issue, which is really unfortunate, is cyberbullying. And this is one of the main uses of some of those anonymous messaging apps that I mentioned earlier. So here we're targeting activists, right? But we have no control over who uses our app. So to address this, we're looking at some questions related to detecting and mitigating cyberbullying. And we've been talking to some psychologists to adapt some ideas from the psychology literature to the digital domain. So with that, I would like to thank my fantastic collaborators and take any questions.
Any questions? We have time for one quick question.
Can you show any results on with the spies the distance between your ML estimate of the person and the truth?
Oh, the hop distance? Yeah.
Like some sort of high probability the distance is at least X or something?
Right, so the distance tends to be very small. We do have results on that as well. And the distance tends asymptotically towards 2 hops, which sounds terrible. But I would point out that in most social networks, 2 hops gets you a lot of people.
Okay, let's thank our speaker. This concludes the first session of the conference. Please join us in the 3rd floor, room 301. We're having a poster session and a lunch at the same time, and then we come back here at 1:30 to continue the next session of the conference. Thank you.